Hey, we've got a Codeforces diff leader on today. Here we go. Let's see, sums of subsequences. Okay. Okay, so that's interesting. This is kind of so A0. We know A0 is going to be B1. We know the sum of everything. And I guess we could take, no, if we take the sum of all, same thing. Oh, the last two is going to be 6. It doesn't. Oh. It's going to be A1, A3. E5. Is that right? Okay, so I think we're good there. It's kind of tricky. Okay. Maybe this is fine. This is how you solved the last algorithm code problem. He wipes one off. Okay. Oh, so here A B B B B. Okay, got it. So yeah, we're just going to if stream.back is not equal to diagrams.0 up front, not equals true string. It's never found, just add like an A. Fine. All right, cool. Paint all the elements into 2 colors. Oh, it has to perfectly alternate. I can just cheese this problem. With poly row. Oh. Oh, maybe not. Okay. There's too many test cases. No, I can totally choose this problem. Just GCD and then. Alright, so you have to be alternating, so you can take. There's two halves you can take. Oh, you should just take the GCD. Like, there's no reason not to take the GCD. Yeah, okay, I see. Okay, no need to choose the problem. Alright, and then true. I don't know what's going on with these gray coders. But they're just way faster than me. Okay. Two elements of the array. Remove them. Oh, remove them in a school. And the remaining elements. Calculate the minimum possible score. Oh, interesting. So you can sort them. And we can just take. It'll be at most one, and we add the smallest remaining numbers. Okay, but can we do better than that? Can we do better than that? We have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. And then that. Oh, that is interesting. It's just kind of the majority. I think it's not worth taking a smaller number. Yeah, okay, so then you're just kind of the majority element. So Not ants, A. What am I doing? Okay, now you're just counting the majority element. I don't know why I'm doing this in your time. There's no reason to do this in your time. Alright, yep. And then most is plus equals most minus size minus most. And it's max extra delay 2 and 0. That's it. All right. And towns range through circles actually. Okay. One concert in each town. Isn't that, they already said that? I'm confused. Okay, this is confusing, but I guess this makes sense. So you're saying 1 plus your guy plus 2 times the previous guy plus 3 times is equal to, yeah. Okay. Oh, you, okay, I see. Take the next thing, this thing minus the next thing, right? It's like, and then the next thing is like AI plus 1 plus 2 plus AI. This minus this. Minus n times AI plus 1, right? Yeah, okay, got it. What is this? This should be divisible by Alright, and now the difference is going to be bi minus b. If result 0 or 1. We're going to alpha vector. That is too many no's. 12, 16, 14. For 2, that is divided by 6. Oh, not, what is this? Oh my god. Can't write code. Oh, just after the minute. I don't know who this is, but G has solves, but not F. Okay, maybe we can read both. These people who did just G. Probably. Alright, let's. Write in binary form without zeros, add 0, 1 to the right. Can you make X? Oh wow, that's really weird. You have 1, something, and the last one, and you have some zeros. Okay, so you can add a 0, which removes that. As long as that is a substring, not a substring. Substring surrounded by 1s. Okay, yeah. think that's right. Alright, so now if x is you have this, and then you also have while not x1, x0. Why does it keep adding the 1? I didn't explore one. Just yes, okay, this matches. If out substring I continue, and then I plus mjson. Okay, let's do it. Okay, so the other things we can do are auto 1. We just add a bunch of 1s on each side. I think that makes sense. All right, moving into first, one more problem. Oh, I see. Oh, I see. I see. Okay, I see. I see. You can get that 31. Once you get 2, now you can do some stuff. You get that 12, you can get that 14, and you get that 31. 15, you can get that 18, you can get that 31, and you get the 15. Yeah, but you can't get 30 and 31 for a while. All right, what's the right outcome? Do you start with the biggest and you just greedily go up? Yeah, you just sort them. Here's some of these are mine, some of these are yours. If I have mine, yeah, just keep jumping while you can. And so once this one breaks, this one goes over to here. Once this one breaks, these two go all the way to here. Once this breaks, these three go to here. Just where it's just. First, everything is blocked, right? And then, yeah, so the one, this one's unblocked. And then at 2, these all become unblocked. With here. Oh, that's not it. And then at 3, this becomes unblocked. So here, here, and then here, here, here. Do I just have to simulate this process with the sec tree? Is that the only thing that I can do? Well, 20 minutes behind. Nice. Can I would here? Wrong answer, wrong answer. Nice. Okay, so I mean, yeah, if I have to, I could simulate this process with the sec tree. Accumulation linear circle. It's a question of where is the next. Is this not overcomplicating it? Mm-hmm. How long is a sequence of ones that? Are the queries sorted? No. Ugh. I mean, I can code this in a way that's it's log squared, and that's probably fine. Alright, so I guess what I'm gonna do is, yeah, so this thing breaks, we remove it, we find the next one, find only ones, and then find ones here, and then move them up. I need a way to like search backwards, don't I? Alright, I can just code this, yeah. Log squared, let's do it. I don't have to be super fast, it just needs to be get smooth. Is this tree already like a superset of what I need? I don't need to set, I can just add. I think we just use this, right? Cool, yeah. Okay, so I don't need maximum. I need some, and then I have some, right? Or items is a little different. That's it, I think. Is that what I want? I guess that's what I want. So, change it to add length. Because if it's like +1, yeah, that's what we need. Okay. That's it. I think that's it. Okay, so list is literally everything's a gap. How are we doing? Yep, okay. Sorted gaps. Sure, no, let's sort it. Okay, and then we have Corey's. So, do we need int 64 for some of these? Maybe we should. For later, while s less than move gap. Okay. That's one tree, subtree, tree. It's just ci dot second plus n. So it's 1 or 0. So what's the second? It's like sum, item sum, full item sum. Full item sum is going to be ci at first. Maybe we don't need. No. Why do I need item sum? I just need this. Right? It's sometimes full item sum. Let's assume you don't want to construct some sort of mid segment, which makes sense. I guess that's fine. Yeah, we don't need to. Dot item sum, right? Now we just remove gap. Okay, what does remove gap take in? The index of gap. Oh, we have 1, 1, 1, 1. We remove this gap. Maybe I need to search backwards. This is actually not concerning. This has so much penalty that it's fine. Yeah, that is so much penalty. All right. Oh, what is forget? That, so next gap gives you an upper bound. Next gap gives you an upper bound where you can move to. From here we can see how many zeros there are. I want to find the last zero. This thing takes 2 seconds. Second A, second B. It takes 2 seconds. So, yeah, this one doesn't matter. It's actually... It should be -1. If last is 0, so press return, otherwise you're going to move from here to here. Yeah, we have to, it's like a reverse. If tree.query from mid to is also return. Otherwise you want low through index. Just to move low through index +1. -1. Is it really? The beat is 147. Yep, okay. And I forgot this. Okay, so remove gap is not doing anything yet. 147, what is that? 81. That is a lot of time. That is a lot of time. All right. 54. Oh, what happened? Why isn't it? Where's gap 2? That's so peculiar. What? Where's gap 2? What just happened? Oh no. That's the problem. Okay. One, yep, 1, 2. 0, 1, 2, 3, 4, 5. Yep, 1, 5, up to 0, up to 1, up 3 at 3, 12 at 4, 6, 0, 6. Yep, those are the gaps. Okay, so that looks good. That is a bad bug. Remove gap 2, remove 5. Oh, I didn't give it a first index. Yep. Okay. Index +1 actually. Plus 0 is 6. Alright, I have the sample working. I can submit, I just don't need to. 139, what is that? 73, so I have another like 16 minutes. That's plenty of time to write a test. Yeah, okay, let's do it. And this, I guess, is just... Just make sure everything that's int should be int. That's fine. That's the index. That's fine. Caps. That's fine. That's fine. Sorted caps. That's fine. Of course, that's fine. It's index. That's an index. These are all fine. Yep. All right. So. Why am I rewriting this? Okay. Actually, we don't do that. If these are going to and these is K. This is a do while actually. This seems right. Okay, so now let's go generator. Let's double check the time situation. Yep. We're at 6, plenty of time. Okay, so we need 4. Output A and then B and then output chorus. Oops. Yep. That's very simple. Maybe like 100, 100, 100. And just run some tests. Oh, mismatch. Okay, let's run some small tests. Maybe something smaller. Come on. Okay. Wait, I can get that thing. Yeah, it should be 1, 3, 4, 4, just 12. Oh no. Do I have time to fix this? No, I'm gonna have to fix it regardless, so. Okay, let's see. We want to revert. Okay. No, it only happens here. Okay, so at 1, yep, that's fine. Move up to 3. The last 0 is at 4. Why is the last 0 at 4? That's fine. We've got a 2. The last 0 is at 2. This length error. No. Alright. Oh, that's why. Okay. So 0, 4 to 1, 5. What? Oh. Yeah, I see. Gaps at lower bound index. If it is not the gaps at begin, what preve it? Low equals max low. Is that what we want? $73 to 15. Yeah, I still have time. Seems good. We have like do a bunch of parallel. I think I overcomplicated this. Yeah, it looks like fast enough. Sure, let's do it. Oh, what did I get? Alright, whatever. It's a lot of tests. Okay, cool. And move to first. Why did that take me so long? I must have missed something simple. Alright. Should have caught this too, that was kind of bad. I do need a reverse search, do I? That's a clean submission record. Alright, let's see. Rainbow doing the rainbow stuff. Oh, E took, or F took him a long time. Oh, I guess F is easy to mess up. Yeah. Let's see. Okay, we'll go over solutions in a little bit. All right, here we are. Still singing first, but let's talk about the problems and the approaches. So, yeah, I realized that my solution for G was very overcomplicated, and there's something much simpler that should work. But that makes sense because I mean, there's people here who solved it in under 20 minutes, so that definitely adds up. Luckily, I still just managed to clutch out the time penalty, even with my worst solution. But yeah, next time I should probably catch that better solution. Anyway, let's go through A through G. So first, problem A. Yeah, problem A I thought was kind of tricky, although now that I think about it, I think I overcomplicated this one a bit as well. So problem A, I think really what's going on is you have A1, A2, A3, right? And then the subsets are in sorted order. A1 should be the first subset, and then actually A2 is the second subset. And the reason is it can't be less than A1 plus A2, which is the smallest sum of 2. Then there's some ordering of A3, A1 plus A2, and then there's A2 plus A1 plus A3, A2 plus A3, and then A1. Yeah, this is always the ordering. It's only these two that could be actually different. So yeah, you can actually do something a bit simpler here than what I did. So yeah, what I did is first I took the first value as the A1, in this case A0, because I'm using 0 based. I actually grabbed this one for some reason. I should really just grab this one. I should really be doing A1 equals B2, and then yeah, this makes more sense. Yep, so this should do it. Oh, no, their examples are just out of order for whatever reason. You know what, let's just submit it, why not? Yeah, so this is kind of a tricky one. Definitely not hard to code, but it takes some thinking about what the order of these subsets could be. Yeah, accepted. We got 0 milliseconds, wow, it's pretty fast. Definitely takes some thinking about the ordering of these subsets. And once you get that, then the code is pretty simple. But yeah, I guess you benefit from the fact that you can submit here multiple times. So you can try out different things, and even if you didn't do it right, you can go back and fix it afterward. All right, problem B. What was B? Oh yeah, okay. So you have a string, and you take all of the bigrams, and then you remove one of them, and then you're given them back in the same order, and you need to come up with a word that makes this. So basically, if you didn't remove one of them, it's pretty easy. You just kind of attach them together, and you skip the repeated letter. So here's just A, B, B, A, B, A, right? Which is this. And yeah, that's pretty simple. The only thing that can happen when you remove one of them is you can have an end of one bigram not match the, or for example, this one, the end of this one, A, doesn't match the start of this one, B, because we removed this one. When that happens, we just, in this case, we just add the full bigram instead of the second character. So from this AA, we'll just add BA, the full thing. And the one case is you can remove a bigram and still end up with a valid sequence where you don't have any mismatches. In that case, you can kind of do whatever. You can just add an A at the end, or a B. Doesn't matter what you want to, whatever you want to add, because we're just pretending that the last bigram got deleted. So yeah, pretty simple solution. Just involves making this observation, and this should only happen at most once, and we're fine because of this guaranteed here. So yeah, that's the solution to B. All right, gonna go through the rest of these. Problem C. Oh, right, okay. So for this problem, you pick a number D, and everything divisible by D you paint red, everything else you paint blue. You want the array to end up completely alternating in colors, and you want to figure out whether that's possible. So yeah, basically, you have to find a number where all the even indexes are divisible by it and all the odd indexes are not divisible by it, or vice versa. So what we want to do here, this kind of screams GCD, right? Greatest common divisor. What we do is we take the GCD of the even indexes or indices, and we take the GCD of the odd indices, right? And then the number we use has to be a factor of one of those, because otherwise it won't be divisible by all the evens or divisible by all the odds. And then if we think about it, let's say we have the GCD of the evens, then we really want to just use that full GCD instead of a factor of it, because that gives us the best possible chance of not having any of the odds divisible by it, if that makes sense. So we really only have two candidate values we need to test, which are the two GCDs. And so here I'm just testing them. Yeah, and so if G0 succeeds, we print that. If G1 succeeds, we print that. Otherwise, we print the failure case, which is 0. So that's the solution. It's, yeah, the runtime is super fast. It's n times log of the numbers. Oh, actually, it's even better than that. It's n plus log of the numbers. But that's kind of a minor detail. It's fine either way. Cool. That's problem C. Problem D. Yeah. Okay. So for this one, you end up doing a greedy approach where for your k operations, you always take the 2k biggest numbers. And the reason for that is for these floor divisions, they're either 0 or 1. They're only 1 if the two numbers are equal. If the two numbers are different, you can always make them 0. And we're trying to get a minimum score. So they can only be at most 1. And if let's say you didn't take the 2k biggest numbers, you could swap out one of your smaller numbers with one of the bigger numbers, and that way you would gain, or you would gain at least one improvement of 1 in your score from the sum of the remaining numbers, and you would lose at most 1 from this, so it can't be worse. And then yeah, once you do that, we're just going to take the 2k. First of all, we add the n minus 2k smallest numbers, because we have to have those. And then with the 2k remaining numbers, we just want to match up as many non-equal pairs as possible. And it turns out as long as the majority element occurs at most half the time, you can do it perfectly. And if the majority element occurs more than half the time, then you can only greedily match and make it work. So I don't know why I counted the elements in linear time. That was kind of unnecessary when n is so small. But I did that, and yeah, then basically if most is the number of the maximum number of the same thing, you take most minus everything that's not that, and that's kind of the extra you have, and those have to pair with each other. And so that's how we get our answer. Okay, that's D. Problem E. What is this problem? Oh, right. This is, you basically get n sort of equations on sums of like 1 times ai plus 2 times ai minus 1 all the way to n times ai plus 1. And so yeah, first thing is we add all of them. You want to get the sum of ai, so we add all of them, and that makes the like coefficients equal. If that sum isn't divisible by the sum of 1 through n, then that's already a failure, so that's a no. Otherwise, we know the sum of all the ai. And then there's one tricky thing where if you take bi, actually if you take, yeah, what is this? If you take bi minus 1, like bi minus 1, you actually get, it's like a sum minus n times ai. And that's what we're doing here. And so ai has to be the result, like this difference divided by n. So that's the key trick here. Basically, if you take two adjacent sums and then you subtract them, you get this nice cancellation property where it's almost the sum of all ai, except for n times ai in particular. So just a little bit of math for this problem. It ends up being a linear time solution, so very efficient. And yeah, you just gotta check some mods to make sure that it actually does work. Otherwise the answers aren't integers. Yeah, and I think that there was this condition which I didn't think too much about. It's probably fine. Yeah, I don't know. It's probably fine. I don't want to think about it too much. Maybe I'll fail a system test. We'll see. Anyway, let's keep moving. Problem F. Yeah, you have two operations. You can write a number in binary form, add a 0, 1 to the end, to the right, reverse it, and then turn it into a decimal number. So 34 is this. You can add a 1 and reverse it, and you get this, which is 81. Or you can add a 0, reverse it, and removing zeros, and you get this. So, well, what just happened? It's weird. It's really weird. Anyway, so basically, once we have our number always starts with a 1. Once our number ends with a 1, if we do the 0 operation, it's actually just reversing the number. That's the only thing that the 0 does. So we can reverse a number, or we can add a 1 to the end and reverse a number. So basically, we can reverse a number, or we can add a 1 to the end. So basically, we can add 1s to both ends, as many as we want, on either end, and or reverse a number. That's true once the number starts and ends with a 1. Notice that if we do the 0 operation, the number will end up starting and ending with a 1. So there's kind of only 4 bases of the number that we can get, where after that we have to add ones on both ends. And that is the original number plus a 1 at the end, as well as that string reversed. And then there's the 0 operation, where we remove all the zeros from the end, and then there's that string reversed. So those are kind of the 4 cases of what we can do with x. And then we can just add as many ones as we want to either end. And so this is what my code does. Basically, it tries to see, hey, does this in string match the out string? In order to match, in has to be a substring of the out string, and then everything else has to be ones. And that's what this is checking. And everything else has to be ones. Yeah, so this is fairly simple logic. You just kind of have to think through the, what does the 0 operation really do? If, except for the very first one, it just reverses the number. It's always just reversing the number, and that's kind of the key here. All right, and last problem is problem G. Yeah, so for problem G, I basically, first I take a sorted array of all of the items. Some of them belong to us, some of them belong to the other character. And you want to track the gaps between consecutive items. So if something has a gap that is more than your value of k, you cannot cross that gap in the sorted order, right? And if it's less than or equal to k, you can cross that gap. So basically you're going to find these gaps, and then you're going to push all of your items up until they run into a gap. I did this in a kind of nasty way where I have a lazy seg tree of zeros and ones and the sums, like, and the item values. And then when I remove a gap, so you want to just sweep through the queries in sorted order and through the gap sizes in sorted order and remove them one by one. When I remove a gap, I find out how many zeros I can push my ones forward to. So ones mean that this is my item, zeros mean that this is their item. And when a gap occurs, basically if you have 1, 1, 1, 1, and then there's a gap right here, and you remove that gap, you can kind of push all of your items up, if that makes sense. If this is like the sorted order of items, right? You can push, once your k exceeds this gap, not exceeds, but like greater than or equal to, then all your items, assuming that's the only gap in this, all right? Then you can push all your items from the 4 smallest values here to the 4 largest values here. That's kind of the main idea. So this does a couple different binary searches. One is to find how far we can push. One is to find how many ones there are. This makes sure, you make sure that previous and next gaps are still satisfied. And then we do an update where we subtract 1 from this range and we add 1 to this range. So that's kind of the idea here. And you also need a set of the gaps. Another option is Fenwick tree. I think a better solution is to just do a union find type of thing where you have ranges that are fully accessible. That means they have no gaps within. And then within those ranges, you just push the ones all the way to the end. And then when you remove a gap, you're combining 2 ranges. So you're pushing the ones from the end of the left range to the end of the right range. And that should be fairly simple. So I think that actually gets you a better, well, I guess you still have to sort. So you still have like kind of n log n complexity, but that is a better and simpler solution. Luckily, I still managed to, thanks to silly ICPC scoring, I still managed to clutch out the win. But yeah, maybe I'll code the solution afterward. Anyway, thanks for checking out this video. If you liked it, feel free to like and subscribe to the channel, and I'll see you in the next one.